Goedemiddag, dames and heren. Good afternoon, ladies and gentlemen. Please be seated. Last year, at one point, I actually forgot it, and I was like speaking for 5 minutes, and everyone was still standing. So now I make a point of having you all seated. So, firstly, you said congratulations, but before I say that, welcome to everybody who's here this afternoon. Welkom vir almal wat vanmiddag hier so is. En dan veral ook vir ons collega's and colleagues and friends who are online. You're also very, very welcome to be part of our proceedings here. So my name is Bekker van Bekker. I'm currently the Dean of Engineering at here at Stellenbosch University. And it's really an honor for me to welcome you here to the Fire and Ice inaugural lecture series at Stellenbosch University Faculty of Engineering. It's not always that, we can say fire and ice, right? So fire and ice we will have this afternoon. I first would like to welcome a number of people specifically who are here, specifically our Deputy Vice-Chancellor, Research, Innovation and Postgraduate Studies, Professor Eugene Tutte. Eugene, thank you very much for making the time available, and we really appreciate that you are here. We also have our honorary speaker, Mr. Fire, which is Professor Richard Walls. And specifically, we want to welcome Maren Walls, his wife, his children, Timothy and Amy, who are not attending, but I'm sure they're watching on the TV at home. Stuart and Jane Walls, the parents of Professor Walls, as well as Philip and Suzette Moser, the in-laws of Professor Walls. Then, if things get too hot here, we also have Deputy Fire Chief Josephus Pretorius from Brede Vallei Municipaliteit. Welkom hierso en baie dankie dat u ons veilig gaan hou vanmiddag. As well as Danielle Antonellis from the USA, who is the founder of the international NGO Kindling Safety, as well as Dean Charles Kahanji of the University of Zambia, and Mr. Paulo Trinchero, who is the CEO of the South African Institute of Steel Construction. Then our, shall we say, Miss Ice? Professor Ice, let's call it Professor Ice, there we go. So Professor Ice, Professor Annie Bekker, welcome here as well, and you're the second star in our attraction this afternoon. And then we also have Dr. Bernard Bekker here somewhere, who is the husband of Professor Bekker. We also have Art and Bertu and Lena, the children, who are not here, but I'm sure they're in front of the TV at home watching us. And then also, I didn't see if Bessie is here, but Bessie, who is an old friend of the faculty, and Magdalene van der Westhuizen, who are the parents of Professor Bekker. And then also, of course, we have to welcome all the friends, the colleagues, the mothers, and the fellow trail runners and king clip deliverers, I was told earlier this evening. So there's a lot of friends of Annie here. Actually, I can see them sitting there. You are very, very welcome, and thank you very much for supporting your fellow trail runner this afternoon. And then, of course, it's also very important that we acknowledge all our colleagues and the students who are here. I think frequently we forget to mention, but I'm sure Richard and Annie will remind us, that the success of our academics depends a lot on the students and the postgraduate students. So thank you very much for the students who are around and the collaborators, and then again, especially the people who are online. So with that, I hopefully have mentioned everybody that I was supposed to mention. If not, Jonathan Deal here in the front will be responsible for that. He's very nervous this afternoon. Okay, so colleagues, we've got two very exciting talks to listen to, and I'm going to introduce Professor Walls first, and then he's going to deliver his talk, and then I will introduce Professor Bekker more formally, and then she will deliver her talk. So Richard is the head of the Fire Engineering Research Unit at Stellenbosch University, which I sometimes think is referred to as Fire Sun. He joined Stellenbosch after a career in industry as a structural engineer, and he really excelled in his academic career at Stellenbosch University. His research focused on fire-related topics, such as the design of steel structures, post-fire investigations, plastic recycling facilities, agricultural storage facilities, so you can hear lots of stuff where there's lots of kindling that can actually catch fire. 3D printed concrete at elevated temperatures, material behavior, and multi-story mass timber buildings, and especially informal settlements fire behavior. And we're going to learn a lot about that, but I think that's a very significant and unique contribution that Richard is bringing to the South African environment. He is well known as Mr. Mythbuster, as he has done a lot of full-scale fire tests on informal dwellings, and around 70 houses set on fire to look at the fire behavior, the spread, and how to reduce the impact of such fires. He was part of the team who analyzed the Knysna fire disaster and investigated why almost 1,000 homes were lost in South Africa's largest wildland fire disaster. He's responsible for a number of students and also started a program, master's and PhD programs in fire safety engineering at Stellenbosch University. His team has published the first technical engineering guideline in the world for fire safety in informal settlements and have contributed to publications by the World Bank, United Nations, and various organizations. He was the recipient of the Emerging Researcher of the Year in Science Engineering in South Africa, the so-called NSTF TW Kambula Awards. Sometimes we also refer to these awards as the Oscars of the researchers in the country, as well as award in structural engineering education from the Institution of Structural Engineers, ISTRUCT, in the UK. So that is quite an impressive bio that we have here, and Richard, we really look forward to listen to you this afternoon, and we are really honored to have somebody of your caliber as one of our colleagues.
Okay, good afternoon, colleagues, friends, family, people online. It's good to be here this evening. So, going to be giving a talk, Fire Safety Engineering, where physics and disasters meet. Now, fire safety, Stellenbosch University has an illustrious history in this field. We've burnt down a men's residence, we've burnt down a ladies' residence, we've burnt down an accounting building, and we burnt down an admin building. So it kind of made sense that we might as well formalize what we're already good at and start getting some academic publications out of it. So I'm going to be discussing through now the work that the team has been doing in terms of fire safety. And so just as a background now to introduce the topic, when I was about 10 years old, we often would braai at home. And I remember one day the braai was going, at the bottom of the weber, these little coals would fall through into the tray at the bottom. And there was a can of spray and cook lying there. And as a 10-year-old, I knew that if you put the wet on the red, the fire went out. And I saw when you used the spray and cook, wet stuff came out. So I thought this would be a good idea. I'm just messing around. I'm going to spray the bottom of these burning coals. Now, I think the fact that some of you are giggling probably means you realize that applying an aerosol-based oil to embers is probably not a good idea. And so that's going to lead me into the hypothesis that I'm going to be exploring this evening, is that just because you can braai, it doesn't mean you're a fire engineer. So that is the main hypothesis I will seek to elucidate in the sections that follow. And the good news is that my father stopped me before I could spray, so thankfully it didn't end badly. But the problem is, in reality, often we have a lack of technical understanding of some of these problems leading to what I may have done to myself far worse than losing eyebrows or wherever it would have met. So going to be looking at different aspects of that. First, we're going to cover a bit of the physics, understanding the physics of fire behavior. And then after that, looking at various areas the team has been working at. First, the informal settlement fire safety, then materials and fire safety, and then structural fire engineering. And looking at when solutions aren't suitable, what it can possibly lead to. So just as a background, studying ignition, the basics. So here we have a sample. There's a radiant flux being applied to it. It's heating up. Only gases burn. So what we first need to do is convert our solid into a gas. So enough energy needs to be radiated down onto our timber, our plastic, our agricultural products, whatever it is, converts it into gases, and then there must be sufficient gases to ignite so that pyrolysis gases are ignite. Now ignition has started, the fire has begun, and now it'll start spreading across the things in the area. Depending on the geometry of the room, where the fires start, that might be fast, very slow. And so this is a sort of typical time temperature curve. You have ignition, bottom left, and then it gradually then grows. You have the growth phase, and then if you've got a lot of combustibles in the area, it'll grow very quickly. If there's not a lot, maybe it'll eventually die out. But then what happens, as it spreads around, we go through this phase. Sometimes it's otherwise a point in time called flashover, which I'll show you shortly. Then it grows, the fire grows, the temperature increases, and we reach then the fully developed fire in the middle. It's burning as fast as it can get, as fast as oxygen can get into the room. It burns, and then after that, decay occurs. So now I'm going to show you an experiment. This is flashover. There is a hot layer at the top, and then a very rapid transition from a localized fire to everything burning as fast as you can get. Even if you're a firefighter in full PPE, you will die in that room. And in an informal dwelling, that can be a minute. From ignition to flashover can be a minute. In a large dwelling, it may be many minutes. I mean, it could be even hours, depending how long, if it's a smoldering fire, etc. And so that's what we're trying to prevent from happening, and that's what we're trying to understand. And then also, once we understand, how can we start guarding against it? And that brings me to the first topic we're going to be having a look at, informal settlements. Now, if you look at the picture on the left and the picture on the right, they're the same. It's just a few hundred years apart. The Great Fire of London looks very much the same as many of our informal settlement dwellings, our formal settlements during a large fire incident. And these sorts of large, devastating fires that have swept through areas have occurred around the world. New York, Chicago, Istanbul, Tokyo, they've all had them at one stage or another, decimating entire sections of their cities. The thing is, with decades of development, formal housing, brick structures, fire departments, codes and standards, good electrical installations, the number of fires and the extent of fires gradually goes down. However, we are where they were hundreds of years ago or decades ago, depending on where in the world you were. And the question is, how do we get from the Great Fire of London to where London is now? And the same thing, how do we get from where informal settlements now to where they could be? At least protecting it, at least reducing the impact. So firstly now, there's a lot of complexity. This is not a typical engineering problem. I do apologize that the video is jumping a bit for some reason. These are very complex environments. When a fire breaks out, it's not that you just send in the fire departments quickly here and done. You've got basically a wildland fire. The fire behavior is very much the same as a wildland, a continuous sprawl of combustible fuel with a fire line pushing through it and tracking and then growing at very high rates. In some of the incidents, for instance, Imi Zamoyeta back in 2017, there were 9 homes a minute burning down at one stage at the maximum rate of the fire. Started small, but once it got going, it just kept pushing through, and that was down a hill. Fires burn faster uphill, and that was burning downhill at 9 homes a minute. And that's the sort of magnitude of disaster that you get. Recently in Bangladesh, a refugee camp that the team's been involved with, there was 45,000 people left homeless in one incident. Same problem, a continuous sprawl of combustible material that a fire line pushes through, and it basically doesn't matter what you throw at it once it gets that stage. You eventually just hope it burns out, unless you have some serious firefighting resources. A fire extinguisher or a few buckets of water is not going to do a whole lot. So how do we start using that to at least intervene where we can? And this is a full-scale experiment. This is 20 full-scale homes, 4 of them where the stars were ignited at once. After about a minute or so, the first line of dwellings have hit flashover. Then it spreads to the second line. So, and these, as I said, these are full-size dwellings that's burning. There is a wind pushing through at about 15 to 25 kilometers an hour. So this is not a southeaster. The southeaster would have pushed this even faster. At about 3.5 minutes, it reaches the third line of dwellings. At around 4 minutes, it reaches the fourth line of dwellings, and then it continues. At roughly 5 minutes, you have 20 homes on fire. It's pushed through. 5 minutes, if you have a remote informal settlement, is maybe when the fire, the call is coming through the fire department, and then they may have a period of time to drive to the incident. Then they may have to go through low-lying electrical cables, people evacuating, blocked roads, and various other challenges to get to the incident. And so we know this is a big problem. We know that this is not ideal. We shouldn't have informal settlements to start with. The aim is brick. But the rate the population is growing, the projection is that our settlements within sub-Saharan Africa are probably going to double or triple around 2050. So if you think Khayelitsha and Nyanga and some of the areas around our cities are big now, wait another 30 years and you're going to see double-story, triple-story, and the likes merging around. Look at the N2. And so if it's an unwanted reality, how do we start addressing it? How do we understand the science? So at least if we're going to put money at it, we're not throwing money down the drain on something that doesn't work. So I'm going to discuss through a couple of interventions: boards on the sides of dwellings, intumescent paints, suppression products, buckets, smoke, and fire alarms. So often after a big incident, now there's 1,000 people, 5,000 people left homeless, and there's a lot of pressure on the mayor, the minister, whoever it is. We need to have a solution, quick, fast. And then people come with their products and they try sell their system, whatever it is, to the mayor, to the disaster management, whoever it is. Maybe let's clad the home with fire-resistant boards. Fire-resistant boards we know work. Let's clad the sides, clad the roof, put them on the inside. That's going to keep the fire out. This stunning picture behind me, as it's frightening, taken by a friend, Justin Sullivan, in a real settlement during a real incident. And notice where the fire is coming. It's slipping through the gap between the wall and the ceiling. The problem is that things such as boards are great for protecting a substrate. You might have a steel, concrete, whatever it is. Those products are to protect a substrate. They're to prevent temperature rise of a structural element. That's not what we're trying to prevent. We're trying to prevent some cardboard and prevent fire spread. So it doesn't matter if the steel sheeting is protected. If we have ignition, the fire spreads. So we don't have a structural resistance problem. We have a fire spread problem. We have an ignition problem. And so often these interventions have mistargeted. So yes, the fireboards are great, but if there's a 20 mil gap around the top, well, it's like a bucket with a hole in the bottom. It's not going to function as a bucket very well. So the same thing now with intumescent paints. And intumescent paint has been rolled out for many homes, hundreds of homes. Various municipalities have spent money. It expands between up to 50 times its original thickness. There's a chemical reaction, and then it thickens. And so it provides a char layer, but once again, it's for structural steel and similar things to prevent temperature rise of the substrate, to prevent the steel underneath from getting too hot. Who cares how hot the sheeting is if the home has caught fire? And so, as I said, quite a bit of money has been spent on this retrofitting homes, which is misapplied. It doesn't prevent ignition. I would rather stick some mud and cement in the corners than to spend products. Now here where it gets really fun. So now, how do we put the fire out? So in our way, we need a reason to burn things down. So we go down, we've worked with many municipalities, Breda Valley much. This was done at City of Cape Town. We burned some dwellings and we burnt them down. And let's see if we can put the fire out. And let's take some of the products that people have been selling to the mayor and see if it works. And there was a couple of findings. First, I didn't miss. I was very proud. I threw lots of things and I didn't miss. So that I haven't lost my cricket arm from school, but also I was standing there with no pressure. It wasn't my home burning, and well, I had another one if I missed. So it would be a little bit different if it was my home and I had one. So that was still a finding that maybe this is not practically suitable. That picture on the screen is a time temperature curve. So the red line is the temperature with time. When it gets to the top and it gets above 600, 800 degrees, that's post flashover. Now, those bunch of colorful lines, that is when we started throwing stuff at it. The first one went in, and this is 600 Rand each. And it's a ball, it blew up, it threw dry chemical powder everywhere. The problem is some of these devices have been developed for small cabinets, got electrical cases, etc. So they may knock out a fire that's this big, but now you put it in a big room, it may knock out the fire locally, but everything is above spontaneous ignition, so the fire just keeps back. So 600 Rand, 1,200 Rand, 1,800 Rand, 2,000, 7 later, and we give up, let's stick the hose on it. So we can see that it doesn't match the needs. It doesn't suppress post-flash over. It may be useful in early stages, but do we understand the limitations? Same thing with those vials on the screen. We threw 24 of those into a dwelling. I was very proud I didn't miss once. 24 in a row at, I think, about 300 Rand each, and those might be invested by the local municipality. So to be perfectly honest, we need to keep it simple. There's my son in his fireman's outfit. This is the Dunoon Informal Settlement. Working with the fire department, giving out buckets. And then Stellenbosch arranged buckets with printed fire department number, because often even people phone the wrong number. They phone 10111. The police have to oblige to go out first and then relay the call to the fire department, extra 10 minutes. But often, if we can't do something, at least putting water, I would rather have a bucket of water than something costing 600 Rand that I know doesn't work. At least after 8 or 9 buckets, we've probably got the problem sorted out, whereas after 10,000 Rands with some of the product, we don't. So sometimes we have to just evaluate where is the level that we can intervene, and what can we do. And my son on the screen there, he was so excited to go with the fire. He wants to be a fireman. Fire engineers are boring, but firemen are cool. So another thing as well, smoke and fire alarms. There are various devices available, and unfortunately, we don't have any perfect solution. And I think a lot of people don't understand the limitations. What you see is a smoldering fire. So this is if you fall asleep on the couch with a cigarette, the fire starts smoldering through the foam, and it releases large amounts of noxious fumes. Now, the problem is with that is there's virtually no temperature rise. You will long die in that room before you even measure a 2 degrees Celsius change at roof level. So if you're relying on a temperature signal for a detector to activate, you will die. You'll be long dead before it goes off. The problem is then we swap over to smoke alarms. Smoke alarms will pick up the smoke, but the same thing in the informal environments, you've got a lot of cooking, steam, various other things, so they experience a lot of nuisance alarms. So I don't believe we have a solution at the moment in terms of detector, but there's a lot of opportunity for moving forward. And I think sometimes simple modifications like putting a lady stocking around a smoke alarm may sort out half the problems we face. So there are ways forwards, and then looking at how do we get the right detector devices in. And then this work has been then put forward. So this is now a free guideline being released by the Department of Human Settlements. So that's now a guideline, and there's brochures in English, Afrikaans, and isiXhosa that's about to come out in the next few weeks for the NGOs and municipalities to then start providing guidance. So often with this, though, as much as I enjoy destroying stuff and there's a lot of academic interest in it, it's not just a personal interest. When I was a student, for about 3 years, I worked with a burn survivor home. And so I would pick them up on a Sunday morning and bring them to church, and we'd work with them, and then various other things afterwards. And the first time arriving at the church, it was like the parting of the Red Sea, when kids without arms and eyes and such, and everyone's like, whoa. Within a few weeks, they were loved and cherished and part of it, part of the community. But there's a lot of things we don't even see. Things that will scar people for life. They don't even appear on a data report. And millions is being spent by our hospitals. If you quantified the medical cost of these incidents, it's massive. If you think how many operations a 3-year-old or an 8-year-old may go through if he has had major burns down his one side of the body or the other, or his face or something, and it'll change them for life. So there's a lot of things we don't even see that influences it. Now moving on to some other areas. For instance, looking at materials and fire safety, and just because you can bride doesn't mean you're a fire engineer. Let's start having a look at the furniture we sit on, eco-friendly homes, which burns better, peanuts or wood. So if you look down at the seat next to you, that consists of polyurethane. If it's nice and soft, it's probably polyurethane. Polyurethane is from oil. You are basically sitting on foamed petrol right now, all of you. So let's not ignite it, let's not get it going. And the scary thing is when you start putting this in many places where there's lots of people. So if you have it in couches, in rooms, etc., many years ago when we had non-synthetics, cottons and leathers and such, you had a lot more time to get out of a room. Now the time to flashover has reduced significantly, sometimes up to half. And for instance, here you can see us burning a couch. And if you have a look at the contents, it was a latex, and there was even nice holes to feed the air through to the burning fire. I mean, you could get a 1 megawatt fire out of a little couch. So that is the scary thing, and that's why you see a Putco bus or something like that go up in flames in a matter of minutes. And the same thing, when you look at the screen, what do you see? I see 500 liters of petrol. And that's roughly the fuel load behind those guys. If you take it, an eco-brick, a 2-liter Coke bottle, I mean, it's great that we're doing recycling, I'm not discouraging that, but it's roughly about 600 grams of content, and it's 600 grams of hydrocarbon-based materials. So that is going to mean this has got the same energy content as roughly half a liter of petrol. So I worked out yesterday, yes, that's roughly 500 liters of petrol on that picture behind you. And if these dwellings get ignited, you have a major, major problem. You can protect them. I mean, this is one bottle working. So yeah, you can see it's flaming. And not only that, if you look at the picture on the right, as it burns, it releases liquid molten plastic that seeps to the ground and then runs. So now you'll have a pool fire developing and spreading out from where you are. So can we get them fire safe? And the good thing is at least you can get some resistance. And the key is in the plaster. So if you build a wall and you now plaster it on the front, if you've got 20 mils or 30 mils or 40 mils, at least you've got a buffer. You've got 20 minutes, maybe up to 60 minutes. As long as that stays in place, you can now actually get a fire rating on a hydrocarbon-containing wall. And so that is at least some guidance that can be put through. If you're going to do this, we need to look at the plaster. We need to make sure that it also sticks, because if the plaster heats up and the plaster falls off, we're in big trouble. So there are ways and means at least working with NGOs and working with companies to try find solutions. And it's the same thing now in any area. We forget how many things are flammable. I mean, peanuts or wood. Are you about to tell me that my bottle of Black Cat peanut butter at home is a risk? No. But if you are now making Black Cat peanut butter and there are thousands of tons going through your factory a year and a warehouse outside, then maybe, because things like peanuts have huge amounts of oil. And when they catch, the question, or the answer to the question is peanuts burn better than wood. If you need a fire, chuck some unshelled peanuts in, and man, it'll get going quickly. The shells get it going, and then it hits the oil on the inside, and you have a great fire. So imagine now you're AFGRI or one of these companies, and you store thousands of tons of grains, of seeds, and the likes. If something like this happens in your silo, you are in big trouble. I mean, that's just going to burn until it burns out. Or the poor fire department trying to put out the fire in a silo. We'll stand back and watch, and then maybe we can sort it out after a while. It's literally that serious when it comes to these big incidents. So the last thing to finish up, just also looking at the application and understanding of these problems in real-world environments. The team's been involved in various things, innovative structural steel systems. Look, how do we use steel? How do we make it into high-rise buildings? So you can use it very safely. Timber. Imagine an 18-story mass timber structure where all the beams, columns, slabs are all timber. That's happening. I'm aware of 2 schemes in South Africa, 7 stories and 4 stories being looked at mass timber, where all the structural elements are timber. This is kind of like your architect's dream and your fire department's worst nightmare. I mean, imagine going to the fire chief in Cape Town saying, hey, can I put up a 18-story solid timber structure? We can do it. Timber chars at a known rate, so we can actually work out how much we lose. But there's still a lot of questions that need to be answered in terms of that. The connections, how do the connections transmit load? So some of the team have been looking at how do we make sure that the connections don't fail, because that's often what the weak point. We've got a beam coming into a column. If that gets compromised, we're in big trouble. And finally, looking at structural fire engineering. Now, this is a real building. The fire burnt occurred there. If we have a look at the column, that's what it looks like now. There is a serious crack all the way through there. And this is critical South African infrastructure. Fire lasted many hours. Stellenbosch is trying to get it up and running, the infrastructure again. So this is a sample. But now this was damaged by the fire, and there were many hypotheses. Now, why did this column fail? Yes, it lasted for a long time, the fire. Was it the material degradation? Did the fire penetrate and cause strength loss in the concrete? Yes, that's a problem, but there's actually a bigger problem that we need to deal with, because if you have a look at it, things expand when they get hot. And so if you have a look at that red beam, it would have been heated up, expanded, and the one place it could release that is on the edge of the building. So it would cause the most movement and the highest forces there. And what you end up with, rather than the material being weakened, and even people were asking questions, was it sabotage? Could it have been damaged? What happened? It was purely the structure broke itself. A very high lateral load from an expanding beam at high temperatures for many hours sheared through that column. A diagonal failure, for all of you who survived third-year concrete design, diagonal failure, shear failure. And that's what it was, about a 400-ton force that beam was able to induce laterally on a column that wasn't designed for it. And so now that has to be repaired. So that's where sort of the structural mechanics gets applied, and then asking the question, now how do we repair these things? So just in conclusions, now fire safety in the world around us. The world is becoming more combustible, whether we like it or not. There is more and more synthetics, bulk storage, big warehouses, huge boxes, high-rise buildings in our cities with large amounts of combustible, large amounts of synthetics in them. Facades, all sorts of things that can burn. So the number of fire safety challenges is only going to increase as the world becomes denser and new products are introduced. And if you think what I showed you on the screen was scary, wait until you see a Tesla car having an accident and those big batteries burning, and big lithium-ion batteries burning. Then you want to see a problem. If you thought an internal combustion engine was bad, wait until you see a big battery bank catch fire and have thermal runaway. So these are the problems we're going to be facing with the future, and we need engineering skills and expertise to protect our cities. We've got to have the people that understand that, I know you can braai, but this is a really, really bad idea that you have right now. And so that's, I think, where hopefully that the university can make a contribution in providing guidance in the way forward. It's never at the core, but it's always on the periphery of problems and things developing, research that's happening. And so with that, as bring this to a close, I'd really like to thank the many agencies that have made this possible, the research and things shown, the Lloyd's Register Foundation, Royal Academy of Engineering, South African Institute of Steel Construction, Western Cape Department of Human Settlements, Engineering and Physical Science Research Council, National Research Foundation, Department of Trade, Industry Competition, various Stellenbosch University's startup funding, ARP, and the like. So, I mean, really appreciate the support that our funders have offered us, and various others also through consulting projects and the like. Supports from my supervisors, Dr. Henny de Klerk and Professor Celeste Viljoen. It was actually Henny who said, I think you should do a topic in fire. He didn't know anything about fire. I didn't know anything about fire. I was like, hey, why not? And the rest is history. And it was purely by accident. It was not anything on my part. I didn't even know what fire engineering was until I found it by accident. Thank you to the Civil Engineering Department for all the support received over the past few years. Ignis Testing down the road, especially Mr. Dirk Streiser, who's been supporting us extensively. They've provided immense support to the university through testing and various other things. Breeda Valley Municipality, they've let us burn down lots of stuff at their place. Western Cape Disaster Management Centre, Mr. Rodney Eckstein, especially, and then his colleagues, Etienne and Malu, who have helped us over the many years, but Rodney really got things going. City of Cape Town Fire Services Training Academy, National Disaster Management, Fire Protection Association of South Africa, because they've really all contributed in many ways. And slowly but surely, this it's gradually having an impact. The red countries are where our postgrad students from. Just Russia doesn't exist, no one comes from there. But the red is where postgrad students are. The blue is people who've attended short courses. The green is collaboration. Really appreciate our students, our collaborators, and the many other people. And hopefully with time, this area of research can spread across the continent, because our continent is far behind the rest of the world. And I'm not going to read all those names, but thank you to all the master's, PhD, postdoc involvement. If I understand correctly, the job of a professor is to take the credit of their students. So I'm taking credit for all the people up there, and I appreciate their contribution. They made this possible, and I showed their screens, their slides, their master's and PhD theses to you and pretended it was all mine. But I appreciate all their contributions. And then lastly, to my family, to my wife, Maren, who has lovingly helped, to my children, Amy and Timothy, who have lovingly hindered, and this family has shown immense support, my parents online and everyone else. And so with that, I'd like to bring this to a close. Thank you, ladies and gentlemen.
Right, thank you very much, Professor Fire. So now it's my honor and a real pleasure as well to introduce Professor Ice to you. And that is Henriette, or as we know her, Annie Bekker. And she claims that she discovered a passion for test engineering and the vibration of structures as a third-year student in mechanical engineering at Stellenbosch University. This versatile field has springboarded her diverse research in topics including dynamic seat comfort in automotive vehicles, where she did some fantastic work for Ford Motor Company, as well as the prediction of bone fracture of vehicle occupants during landmine blast events for Armscor, and this was, I know, her PhD at the University of Cape Town. She then spent quite a number of years working for Optimal Energy. And if you don't know Optimal Energy, that's the company that developed the dual electric vehicle, where she worked on noise and vibration and harshness, as well as the noise and psychoacoustic responses that compose a positive driving experience for the emerging electric vehicle market. She joined the Faculty of Engineering at Stellenbosch University in July 2011, where she has now been a professor since 2020. She has led multi-sensor measurement campaigns on the heavy mobile equipment of a fleet for Richards Bay Minerals, as well as polar vessels, including the South African SA Agulhas too. So whenever the SA Agulhas go somewhere, you know, Annie is kind of hanging on there, or she's waving for us. You're going to tell us about this year's trip as well, I guess, right? Fantastic. As well as the German Polar Stern. Presently, her work proposes to reap novelty from the niche created by digital twins, where operational data is fed to engineering models. These increasingly rapid insights deliver information that can enable managers and operators to make better decisions about the management and operations of their assets. She's a registered professional engineer with the Engineering Council of South Africa. She's an NRF-rated researcher. Her publishing record includes 24 journal articles and 38 articles in academic symposiums and conferences. She is married to Bernard Bekker, as I said already, who is here, and she's the mother of 3 wonderful children, Art, who is 9, and the twins, Berto and Lena. So, Professor Ice, we are ready.
Thank you so much to everyone for being here. It is really a great honor for me to tell you about what you can tell from the way that a ship shudders on an icy wreck hunt. It's also quite appropriate since I seem to have uncontrollable shuddering. I have to start with thank yous. It's been a wonderful career, a wonderful time at the university with so many opportunities and places to springboard to, and it just never seems to stop. So to all these companies who are important, who have esteemed European and South African men, who would take the time to help a random girl from South Africa, thank you very much. And perhaps some of you are online, and if I start mentioning names, I'm definitely going to forget someone. I would also really like to mention other women and mothers. Like, I'm going to lie if I say that it isn't a struggle sometimes to go flat out for work and to feel like you are neglecting someone. But you know, I realized, especially on this open day this year, when people were asking me, like, should women become engineers? I think so. If it's what you love, then that is what you do. And do you know why I think it's possible? It's because you're not alone. And if you think about it, you can't be a successful mother on your own. You can't be a successful train driver on your own. Whatever we do need support. And I think in engineering, the same is true. I have to say thank you to my husband. By not with you, life is an adventure in a Land Cruiser. Yeah, and thank you for never asking me to do any less. And my kids, here they are. How can I leave them on their own? I don't know, but I believe that they are remarkably resilient. And I was the daughter of a mother who worked really hard and who started a medical practice at the age of 50. And my children built boats. So, let's see. Right. I would like to make a map of where we are going tonight. Firstly, the voyage will lead us to why I ended up in engineering, and then talking about our wonderful South African polar supply and research vessel, the SA Agulhas II. We will then take a diversion into history and culture, heaven forbid, and speak about a polar explorer by the name of Sir Ernest Shackleton. This story underpins the significance which I will try to express tonight, and also gives the background to the Endurance 22 expedition. This is a very special expedition I was part of at the beginning of this year, and in this expedition, our ship was navigating in the heavy ice of Antarctica. Instead of trying to avoid it for logistical reasons, it was actually going in there. So I want to look at propeller vibration and also how this ice-going ship handles the crossing of the Southern Ocean. And then I'm going to try to draw it all together in a conclusion. Only 7 chapters and 77 slides in flammable seats. So, have you ever thought why you ended up in the job that you are now? Or been somewhere and try to think back, like, how did I get here? For me, it started on crisp Benoni mornings. It is early and my dad is driving us to school. I can still remember my legs sticking to the black leather seat and the anticipation of me and my brothers, Adrian and Artu, as we stop at our favorite traffic light. We are the only car on the road, and ahead of us is a long, double-laned tar straight that goes down the hill, makes a sharp left with a banking angle. The countdown begins. 3, 2, 1. The car squats down and surges forward on the green light. I can feel the vibration through my body, and my eyes are glued on the speed dial and the stopwatch. And we are doing our first 0 to 100 acceleration test for the day. My dad brakes sharply, as we negotiate the turn. We edge him ever faster as we reach exhilarating speed. Every day, my day started with a vehicle performance test. How could me and both my brothers not end up as mechanical engineers? I have to say that I'm not naturally drawn to internal combustion engines, and that the beauty of helical gear systems has evaded me, and sometimes still continues to. And I think the reason, or where I found my field or my place in engineering, is probably thanks to my mother. Because, in the evenings, we would be practicing music. I would be playing violin, and my mom would be on the piano. And in the beginning, we would abide by all the rules of the Suzuki Violin School. And soon, as we become better and better acquainted with the music, if it was fast, we would race each other to the end. And sometimes we would have fun and completely over-dramatize a piece. Later, I learned that my music sounds great if I practice on my own in the bathroom. And music is a science of precision. Like engineering, it has rules. But the same piece changes into music through interpretation and the way you excite an instrument. So here is a start of Tsardas by Monty. A bland, clear, perfectly correct, open sound. Okay, you can hear that sounded different. Maybe with a few months more practice, we could give that really a gypsy feeling. And I would learn the reason for this in the third year in my mechanical engineering class. And also, the teacher was a very special supervisor of mine, Prof. Bekker. So you see, just like I have my bow exciting this violin instrument, over here there is a metallic plate that is excited by a shaker with salt strewn on it. This note is the excitation of the frequency. Makes these beautiful shapes. And if you listen, you can really hear how the sound climbs into your ears at these beautiful shapes. Okay. So the same excitation causes a different structural response at different frequencies. And these special frequencies that have these beautiful shapes tend to climb into your ears. And this is great if you want to design a musical instrument, but it can really bite you if you are an engineer designing a structure. Sorry, Richard, I'm specifically using a civil engineering example, like the Tacoma Narrows Bridge. So this is the bridge on opening day. And at this point, it looked like the build was successful. But a mere 4 months later, a very high wind was channeled through the narrows of the Tacoma Narrows Strait. And this excites a twisting, and you must remember this twisting mode now, like a torsional mode in the bridge, which is absolutely devastatingly scary and also very expensive, because the bridge collapsed only an hour later. There were a lot of people that agreed that this design would fly. So this is what one also calls emergent behavior. And the thrilling thing about vibration is that there are people dealing with emergent behavior that come and speak to you about exciting problems. We've already spoken about the fields I have been involved in, and I would also like to acknowledge my supervisor at the University of Cape Town, Professor Gerald Nurik, and Professor Skalk Cook and Dr. Trevor Klutter for their assistance in this time. But today we will speak about the darling of South Africa, our Red Lady ship, SA Agulhas II. Let's take a look at this short documentary.
Antarctica is a desert, the driest, windiest, coldest, harshest place on Earth. It's almost twice the size of Australia and colder than the Arctic. The temperature gets as low as -90 degrees Celsius and wind speeds as high as 300 kilometers per hour. Summer days are 24 hours long, and in winter, nights can bring an entire month of darkness. Maintaining a base in Antarctica poses huge logistical challenges for the transportation of personnel, equipment, hazardous cargo, and supplies. For close to 35 years, the South African Department of Environmental Affairs Research and Supply vessel SA Agulhas has been the lifeline to operations here and on Marion and Gough Islands. With the SA Agulhas reaching the end of its working life for such punishing conditions, DEA took the decision to replace its flagship with a new purpose-built vessel to take over these duties using the latest technology. This ship would have to be a tanker, cargo carrier, passenger ship, research vessel, helicopter carrier, and an icebreaker. Such a vessel has never been built.
The ship comprises 26 what they call grand blocks. Those are big structures like the one behind us, and then the ship is constructed in the building dock.
A major milestone of the build is the installation of the ship's engines. 4 6-cylinder Wärtsilä 32 diesel engines make up the main power generation system. Each engine generates 3,000 kilowatts of electric power for the two 4,500 kilowatt electric propulsion motors, each driving a variable pitch propeller.
During 20 weeks, we have lifted all the blocks, so putting those 30 blocks together, we have created this complete shape of the hull.
All scientific equipment must also be demonstrated by manufacturer representatives. A drop keel can be lowered through the bottom of the ship to a depth of 3 meters below the keel. It houses the transducers for measuring the density of plankton layers, small fish, and ocean currents. The large environmental hangar door can be opened at sea to facilitate the operation of deep water probes to a depth of 6,000 meters. A hydraulic A-frame on the stern allows for towing sampling nets and dredges and deploying or retrieving current meter arrays. A moon pool extends from the environmental hangar down through the ship's hull. It can be used as an alternative launch area in pack ice. The shape of the bow is critical for breaking ice. The bow was designed in Rauma and refined by subsidiary company Aka Arctic in Helsinki. This engineering would now be put to the test as the vessel is taken north to find ice during the ice trials.
And this was the point where I became involved with the SA Agulhas II. I can remember being 5 months pregnant, and in the March of that year, traveling with my brother, who was still busy with his engineering degree and was the test engineer at the department, and a small case of vibration sensors to go and participate in 5 days of ice trial testing. At this time, it was my first time on such a big vessel or in any such type of project. Today, the ship is equipped with more than 200 engineering and research sensors. This relates to the vessel responses, the experiences of people on board, and also the weather conditions of ice and waves that surround the ship. Today, I will only be talking about the vessel responses and a little bit about ice. You also saw that during the build of the ship, engineering models were developed that look at the flow and of the ice and the waves around the hull. Now, one of the emerging technologies in Industry 4.0 is that of digital twins. And the broader scope of our project is to develop the SA Agulhas II as a flagship for Vessel 4.0, where we feed data that we measure into engineering models, and through that give new insights to operators with decision horizons on a strategic, tactical, or operational time scale. Okay, at this point, we're just going to take a detour to polar explorer Sir Ernest Shackleton. It's very difficult to explain the significance of the Endurance 22 expedition without looking at his history. You see, Shackleton had a dream to conquer the South Pole. He was part of 2 expeditions, one in which he was a member and another one which he led, to try to be the first people to reach the South Pole. And if you read the history, they both times, they failed and they barely survived on account of being frozen and starved without food. The pole was snatched from Shackleton by a Norwegian man with the name of Roald Amundsen, and he swore that this would not be the end of polar exploration. So Shackleton gained support for the Imperial Trans-Antarctic Expedition. So this is the continent of Antarctica, and Shackleton's plan was to approach the northeastern side of the continent with the Endurance. He would have a second party arriving from Hobart to the Ross Sea. Both these parties would lay food depots for an Antarctic crossing through the South Pole. Shackleton chose to recruit some members for his expedition with this wonderful ad in the newspaper. Men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in the event of success. Sir Ernest Shackleton. The ship set off with 28 men on board and became beset in the Antarctic ice of the Weddell Sea for 10 months. So this is in summer, and in winter, the sun never comes up. And this is a beautiful photo by Hurley in the complete darkness. Yeah. In November, the Endurance was crushed by the force of the ice. Makes like a clock-like cyclone type of movement that crushed it. And I had a look at Shackleton's diary on this day, and his handwriting actually changes. It's like you're home. If you are in the ice and you're standing there and your ship is gone, there is nothing. And this is the level of despair. On board was Captain Frank Worsley, an amazing navigator, and he used an instrument called a sextant, with which he kept detailed records of the ship's drift in the ice. And because of these records, there is a detailed coordinate with the last known location of the Endurance wreck in the ice before it sank. Enter the Endurance 22 expedition, sponsored by the Falklands Maritime Heritage Trust, to which I'm very thankful. And this expedition would aim to locate and survey this wreck of Sir Ernest Shackleton on the seafloor. The Weddell Sea is plagued by multi-year ice, i.e. the ice does not melt. It's one of the most sparsely navigated areas for ships on Earth. And it's expected that the ship would be several kilometers underneath the ocean surface. A very challenging wreck to find. But we set off on 4 February. It's myself and 2 postgraduate students, James John Mattia and Ben Stein. And we are traveling in baggage class. You know, if you read some of the articles, it sounds like we discovered the wreck on our own. In fact, we were just there doing research. Like we were using the fact that the ship was going there to make some nice engineering measurements. So the first task at hand was to cross the entire Southern Ocean. Have you thought about that? Like going in a boat across the sea. It's like driving with your windows open all the time. It's absolutely magnificent. Yeah, like being a dog. We navigated to this intermediate waypoint at the ice edge. So all those colorful stuff is ice, and the purple means the ice is 100% concentrated. If you look a little bit further south, you can see that it wasn't that far to get to the Endurance wreck site. And just to give you an idea of what it looks like, this ice is not very highly concentrated, but such a beautiful photo. and video by my student, James John Matteo, which also has a bit of vibration, I see. But you can see the pancake-like structures, which are ice flows. So they are important in vessel navigation. And of course, you're going to encounter the least resistance if you are navigating through the leader lines between the flows, like open water parts. And this was a major privilege, that through the German Space Agency and Drift and Noise on board, we had access to this amazing ice information. Every day we received a weather update and a detailed map of what the ice looked like. And if you follow my pointer here, that is the Inaugural 2. That is how good the information is. That's very different from what Shackleton had at his disposal. Oh, my department head left. But he wanted me to put in leave. So in my defense, I thought I'd put these few slides in here. So while we are navigating in ice, we, as a team of 4 people, observe the ice conditions around the clock, 24 hours, to see what the ice thickness is, the flow size, the ice concentration, because what we measure makes no sense unless we know what environment is causing it. There's also a very nice example of international collaboration. Jaco Laas is sitting in front here, test engineer in the lab, and they actually built this crane structure for this orange instrument that was coming from Germany. It's an EM device that measures the ice thickness as the ship is moving. We're also managing all our sensors on board, making data downloads, checking that the data has good fidelity, and here we are performing it's almost like listening to the symphony of the propulsion bearings measurements for our collaborators in Germany at RWTH. And then because you're sitting on the bridge, you can see the wildlife going by. And there is a lot of it, and it is amazing. And you should imagine the wind, like there's always wind, because the ship is moving. And finally, we would reach a location, so it was not once that we stopped many, many times, in the ice where they would kick off the search. And these penguins are so inquisitive, they come right up to you, especially if you have hot chocolate. This is a part I'm not allowed to say too much about. We're going to have to wait for the documentary on National Geographic. But this is an AUV. It is a search robot that can dive underneath the ice and in the water very deep. And we use this A-frame, and the other thing is the Inaugural is such an asset that it has these equipment that enables this type of work. But the AUV is launched, and all the while, it's attached to the ship with a tether. So the data keeps on reaching the vessel, even if this AUV is lost. Because the thing that you really want is the data. So unfortunately, that's all about that. And when the AUV is diving for 8 hours, as soon as it's on course, we can get off and study the ice. So a lot of leave I was having. And this is an example of Professor Yuka Takuri at Aalto University. We've been working with them for 10 years. And I also just want to acknowledge Prof. Penty Kuyala, who has retired now. But these ice cores, we look at the temperature, salinity, and also the density of the ice, and that tells us about the strength of the ice surrounding our vessel. Then why were we really there, especially for the propellers in ice? And you'd think, with a long history in ships, that engineers would have figured out propulsion systems by now. But even in open water, so not in ice, just in open water, just in the first world, we still get disasters. And here is an example from a cruise vessel that ran into trouble off the coast of Norway. The oil levels fell very low, and the engines cut out.
A rocky moment for passengers on a cruise ship off the coast of Norway. The Viking Sky was carrying more than 900 holidaymakers when it suffered engine failure in rough seas in the region of Hustadvika. Rescue services airlifted more than half of them to safety. Local authorities were there to welcome them onto dry land.
You're hoping they were not going to get sued. No. But the thing is that propulsion failure is disastrous. You lose control of your ship. And in terms of ice navigation, the use of the northern sea route. It looked like there were more and more voyages every year. That was before COVID. We'll see what happens now. And in both polar regions, Antarctic tourism is really flourishing. Sometimes it's doubling or tripling. It's now almost 50,000 people per year in Antarctica. And most of those people travel on new polar expedition vessels. The thing is that if you damage your propulsion system, you're first going to damage, bend or break a propeller blade. And did you know that engineers have never really measured the loads that we encounter when we travel in ice? So when we're unsure, what we do is we just put in a nice big safety factor. That means extra structure, extra power, and extra money. The thing is that if you do lose your propeller in the ice, it cannot be repaired right there. So you have to hope that maybe on your other propulsion shaft you have enough power to limp home, or you have to be towed and assisted by another vessel. Because of all these uncertainties in ice, very privileged to be part of a project funded by EU Marterra in collaboration or co-funded with the Department of Science and Innovation. It's called HealthProp. It's about the life prediction and health monitoring of marine propulsion system under ice impact. Sounds very sophisticated, but it's a big privilege. And there are lots of PhD students from Norway and Germany now working on the same project and learning so much at quite a fast rate. On Endurance 22, our job was to look and see if we wouldn't be able to really measure these propulsion loads. And this is the lookout. The white cross is the location of the Endurance wreck site. The red is the no-go zone. In this no-go zone, it's likely that we would encounter multi-year ice of 100% concentration. And the limitation here for our ship is mostly because of the strength of the propulsion system. The hull has been additionally strengthened. The propulsion shaft is really long. It's about 30 meters wide. So it's maybe like twice the length of the front part of this hall. And we cannot place a sensor there because it's like putting rocks into your egg beater. Ding, 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 ding. The sensors will not survive. So we measure where it's very safe at an inboard location on the shaft. What physically happens is, remember the twisting of the bridge? The shaft is also doing this. So where you measure is not equal to what is happening at the propeller. And this is where the mathematics comes in. This is what the measurements look like on the shaft. Maybe interesting to say that we have a zebra tape there. It's black, white, black, white, black, white, and exactly measured. And because if you can measure the time, you can measure the velocity. So you can even measure the change in the speed of the shaft as it's rotating by. Very interesting stuff. Here's an example of a lump mass model. So it is a type of model for which we have mathematics, where we can measure on the shaft and calculate the unknown propeller loads. I'm very proud of this because, you see, if you measure, then you have to solve an inverse problem. That just means instead of getting a force and then seeing how the structure responds, you have a response, and now you have to figure out the force. It's basically doing the problem the wrong way around. But this red block, regularization, this was the problem. Because you see, on the left-hand side here, we have a blue curve. That is the zwing, 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 zwing of the shaft. Now we want to know the ting, 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 ting of the propeller that is going to cause that. And you see, it's for 10 revolutions of the shaft, so that's maybe like 5 or 6 seconds. And we can get the red answer after simulating for an entire morning. Whew. Yes. So this will really not give you any real-time intelligence. There's no way that captain will ever know that he has been in danger. He will already be calling in the fire department. So here is this new idea. It's not even new. And it's like the bucket. Sometimes the real solution to an engineering problem is very simple. The equation looks big, but you know what it actually says is for a long shaft, us as mechanical engineers and the physicists and the clever people before that already know exactly the shapes that a long shaft would have, especially if it's made of metal, and to expose it to ting, 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 exactly. And through this, nice, beautiful piece of mathematics. We can produce this Mona Lisa. Can you see that she is, I don't know, 2 days long? You know, we sample at 600 hertz. That's 600 samples per second. And this algorithm can do it, baby, like almost in real time. You can see Nico de Quicker's name there. Couldn't do all the maths on my own. But the regularization has been cancelled out. Okay, so now we can finally actually calculate the loads. Yeah, and also thanks to my PhD student, Brendan Nickerson. It's like a thrilling life ahead of us in this field. Okay, so what we want to know is, was the Aeschylus 2 in danger? I have to get to the point. The shaft can actually handle 1,007 kilonewton meter. And we measured 950 kilonewton meter as our maximum. It's like 5 or 6% safety margin. It's quite close, quite close. We found out that reversing is the worst culprit. It pushes all the ice into the propellers. And, you know, we had some navigators on board that just embraced this new ice information. They're like, yes, give me these satellite photos. I want to have Google Maps for ice. I'm throwing a left here and a right, and I'm going through all the leader lines. And we could note who was just going like straight for the next waypoint through all the ice flows, and who was going through the leader lines. And the interesting thing, I don't know why my chart looks so ugly, I'm sorry, is that you get less of these high loads, like 28% versus 72%. So it seems that this access to data and Mariner 4.0 and the whole hype around that can make a difference. Okay, yes, I know. Less is more, but there's still more. There's a very interesting fact here. You know, we've been looking at the ship now. Here's 7 years of data. The light blue is the amount of days our Aeschylus 2 spends operationally busy in ice. The dark blue is how much she is working in open water. And she was designed with a lot of ice considerations. So let's take a look at what happens to her in waves. She has a spoon-shaped bow, and that is needed to break ice. And you can expect, you know, like if you make a belly flop, like a nice rounded shape, it is going to hurt a lot. And there will be many wave impacts, especially as the waves get higher and higher. The stern of the ship was lifted slightly out of the water to make the resistance less, so that the ice can also pass through seamlessly. And then, like, complaints about wave slamming really started to emerge in 2013. And this was especially because of stern slamming. And despite an attempt to put in a warranty claim, our Department of Environmental Affairs, Forestry and Fisheries was not successful in getting any action. And we have since then continued trying to study this stern slamming and whether it is actually bad for the structure or not. So again, what do engineers do when they design ships? Your ship is designed to remain stable in waves. I'm just like showing this model because we have it, and I'm very proud of the Aeschylus just pitching in the motion of the waves. But you can imagine her rolling, and you don't want your ship to roll over on you. So the stability is accounted for in calculations and quite well understood. Also, the ship is designed to carry load. We heard, like cargo, fuel, passengers. But as you are navigating through the waves, it's like you're riding on a long beam with supports that are shifting. And the ship is hogging and sagging like this. And you can imagine if this was a plastic ruler, which I've since my last presentation stopped to use, you can see that it would, like there would be a little white mark there. And that's because of structural fatigue. And this is accounted for in ship design, the hogging and sagging. But what happens when you are slamming the ship, sorry. No, it's just a support. I'm moving out of the camera, but you know, it's like a jelly-like behavior, a jelly-like motion like this. So it's still the same fatigue, it's just happening much, much faster. And this is called whipping. I love it, I love the name. And this has already caused 3 ships, look at this mole comfort that snapped in half. And they think it was because of whipping. And look at how big that structure is, just look at it. And stare, like an eye test, down the red box. you see that it's visual, jelly-like deformation of massive steel structure. So on the SA Gallus II, we have especially the slamming at the stern of the ship and the water also rushing onto the aft deck. And you know that South Africans really like to braai. So this additional deck space is used for braais and also for mounting container vessels. And this type of waves rushing on board is rather unpredictable in some cases. The really important work on the SA Gallus II is actually done by oceanographers with real problems like global warming. And here is an example of a CTD instrument being deployed off the side hatch. So people are aware of the hazards. You can see the chain there to prevent people from walking across. So the question is, can data help people to predict these situations better? And in terms of shipping, like what about the whipping responses on the fatigue of the structure? Because look at this, we are seeing visual cracks on the ship, on the forward part of the hull. And these cracks are also being repeatedly repaired. Apparently this happens in shipping and the people there are very tough and they are not too worried. But there is something for us to research and monitor. The final technical part I just want to talk about is that we have equipped the ship with an engineering nervous system. So the whole hull has these distributed sensors and they measure acceleration. So in standard 7 grade 9, F equals ma, Newton's second law, acceleration is an indication of force. And acceleration can also be transformed into displacement. So exactly what I was talking about. You have the impact and you can see the shape of the ship's structure. This is what it looks like in the time domain. A whack and whoop, 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 whoop. That's what happens. We can see that the forward part of the ship basically hinges, like from that superstructure. And I'm liking it that there's lots of civil engineers here that are going to become involved. And I've made this slide very much more open to show that we did a test in the same wave state. So we had the ship being slammed from the front and the same waves slapping the ship from the back. And we looked at the number of slams. And you can see the left-hand picture, the blue dots are very close to the 0 line along the vessel length. So there are not so many blue dots, and the magnitude of the acceleration is quite small. Not so when the waves are coming from behind. Impacts are bigger, and there are much more of them. And because of wonderful mathematics and fatigue calculation, the red part is the that engineering methods do not account for. 98% of the damage on the SA Gallus II is caused by whipping in this specific wave state, when the waves approach from the back. For this reason, the SA Gallus is now a case study of the International Committee of Ships and Offshore Structures, where we want to look at better methods to predict and monitor whipping fatigue. Conclusion, you've made it. Oh, yeah. In the past 10 years since we've been involved, 32 collaborators and students have traveled on the SA Gallus II, and they have had the privilege of doing their research on this vessel. Their degrees often take quite a bit longer, and they have to go the extra mile. There's a lot of crawling in ship structures, difficult social circumstances, unpredictable factors that these students have to deal with. And I really believe in that, because I believe that this is the extra mile in terms of developing them as graduates. And the output of that purging of having a bit of a tough time, like when you see someone really deliver on that, it's an amazing feeling of accomplishment for a student, and it transforms them for their life ahead. I wrote this in my teaching portfolio, and I think it missed the mark. But, you know, there's one thing, it's like playing music according to the rules. If you want to build a ship, you can drum up people and all the materials and have the plans. Or alternatively, you can give people a desire, like for the immensity of the sea, to get to the other side, no matter what. So it's this combination of challenge and passion and the thing that comes out when you are really, really, really in a tight spot. I'm thinking of changing this ad next year for postgraduate recruitment. And I really want to get back to the story of Shackleton, like the extreme capacity that man actually has to survive the elements. And the elements are not just out there. They are sometimes in our houses, like in difficult situations, in our students dealing with COVID, in the math that you just do not understand, in this feeling of inadequacy that you have that just doesn't want to go away. It sits there. And here Shackleton's men, like after so much disaster, the ice is melting around them, their ship has sunk, they're pulling this survival craft across the ice to open water. They sail for 5 days to get to fast land, this inhospitable elephant island, a rock with nothing much else. Shackleton realizes they will not survive, and him and 5 other men take the James Caird to travel 1,300 kilometers across a stormy southern ocean to reach South Georgia. Did you know that they still had to cross a 2,000-meter high mountain and hike like for a really long time in ice and crevasses to reach this whaling station at Stormness? And even after this first human contact, it still took not 1, not 2, not 3, but 4 attempts to get to this picture 137 days later when these men are rescued. You know, we are very, very far from this, like, survival. We are higher up in Maslow's triangle. Like, we are in self-actualization. But I believe that in terms of training for our students, that with the world changing, climate change, poverty, war, that this situation may change. And then I want to get to this, that if Shackleton had stopped at any point before his 4th attempt to try and rescue these people, the story would be very different. If he didn't have other people assisting him, if he didn't have a talented navigator or a photographer, he might never have made it. If he didn't write in his diary about his findings, so it's like our research articles, no one would have known about this story. And it says to me, don't give up. Just don't give up. And to be on a South African ship with a South African crew, after failing in 2019 to locate the wreck of Shackleton, the Weddell Sea expedition, to see this is just incredible. You can hardly believe that you get to live through such a moment. And I think that my highlight is for sure, like these golden letters at the back of the ship. And I think that is my message. You know, might we find worthy topics to pursue, and might we do that with passion, and might we find endurance. Thank you.
Well, good evening, colleagues. Good evening, ladies and gentlemen. A word of congratulations to both of you for very, very good presentations. I've got a few take-home messages, and I won't take long because I know that we've got some refreshments outside. But Richard, when I started listening to you, and I'm a keen fire maker myself, and I've got 3 grandboys, little boys that also like making fire. But the little girl will start, I'm sure, soon. But by the way, these fires that you mentioned on campus was in my time during the past 10 years as the DVC. So I was really very interested in helping you build your career. And I'm happy to see that it's coming to fruition this evening. I also couldn't help but think when you spoke about using this, I like also with these grandchildren of mine to look at the science of stupid. And it reminded me a little bit of the science of stupid and also many of the other examples that you mentioned in your presentation. But really important work for us to understand how to, in a world that is changing, and as you say, becoming more easy to set fire, how we navigate our way there. And I think the technological interventions that you mentioned there can go a long way to help us to mitigate some of these risks, especially in informal settlements. I always wondered, how is it that these fires spread so quickly in an informal settlement, and after your talk tonight, I fully understand that. I'm also very pleased to learn that my 1962 Jaguar Mark II is a safer car than a Tesla. But again, thank you very, very much for an exciting presentation. Annie, you had me on the edge of my seat, basically, from the minute you started to talk. I was wondering, what is the violin going to do here? And then you started talking about resonance. We know from as a microbiologist that every cell has got a particular frequency that will kill a particular cell. Now, it seems to be that the same applies to ships, that we just call it by different names, whether it's a whip or whether whatever. But it was fascinating, first of all, in response to the advertisement of Shackleton and also yours. Before I forget, I must just let you know that I'm not coming along. But incredible journey to do so much work on groundbreaking work, looking at all your publications that you cited on your slides. One, sort of would have expected that by now that we would have known quite a bit of that. But we don't. And I think the reason being that these are extreme conditions in which you test these vehicles, and in particular the ship, and everything that goes along with that. I must say, I also, I'm not so keen anymore on going on cruises. If you think of these massive structures, which basically are very vulnerable, if you think about it, in the wild, and which is unpredictable. But I take my hat off to you and your students for actually doing the work that you do. And going to these extremes, actually, I'm sort of starting to think of you as an extreme scientist. That you venture there and that you make these massive contributions. We're very proud of that. So to both of you, congratulations. It's great to have you as full professors here at the university. I don't need to burn down any more buildings here on campus. Thank goodness, Richard. And good luck with your futures. You've got great futures at this university, and you can count on the continued support from my office and from the senior management in this faculty. Much appreciated, and thank you very much. This to you.
Colleagues, is it on? Colleagues, it's my privilege really to make an appearance here on this illustrious stage this afternoon to say thank you on behalf of the faculty. And the most important people that we need to thank are our two wonderful speakers. I think it was really fantastically engaging and enjoyable to listen to both of you. I know both of you also personally for a long time, so I would like to circle back and say a little bit more about each of you from that perspective. But before I do so, can I also thank our Vice Rector for Research, Innovation and Postgraduate Students. I got that out of my head without even looking at the paper. I hope I got it right. Professor Eugene Klute, who has also served this university for a decade in this position and is soon handing over to a new Vice Rector in that position. But Professor, thank you very much for making time for us here, and I'm sure it was a privilege to make the comments that you did on these two excellent candidates. But also, at the same time, we know that many other people are working behind the scenes, so I would like to recognize them as well. Jonathan, thank you for coordinating the publications, some of whom must still be written. Thank you to Amira and Olivia for arranging everything, catering, invitations, and a lot of other coordinations, photos, etc. Thank you for that, and for pitching up always with beautiful shoes and all your professionalism. We tend to take that for granted, but thank you for that. To Justin, thank you for this live streaming and flustering me for a moment. Thank you for the live streaming, for sorting out all the IT and technical things to make the live audience possible. Who am I forgetting? Thank you to Professor Wikus van Niekerk, the Dean of the Faculty, also for introducing both candidates. And then also to Marilee Oberholzer for coordinating from the faculty side. And also thank you to Ulrich and Clint for getting the venue ready. That is it in terms of the official thank yous. But I want to circle back to both candidates and just say something very short. I'm a huge fan of both of them. They are each genuinely brilliant people, and they have their own unique strengths. And I want to just say thank you so much for showcasing some of your work here tonight. And Richard, you've always impressed me with how many things you are genuinely good at and how many of them you can do at the same time. But maybe your most, from my view, and I might not have it perfect, but you're very, very good at really channeling your many talents, but channeling them in a way that really produce impact. I think you are excellent at optimizing, and so thank you for bringing your talents and your skill to this faculty and for serving us and the greater community with them. Thank you for that. And I just want to say, his talents go much wider than academics. He also used to play provincial tennis. I'm not sure how much time you have for playing tennis now that you have such a family life to maintain, but also he's very involved in charities. And in fact, he also has a theology degree. So of the many other talents, I just want to make mention. And even when I met you 15 years ago or more at some conference when you were still a master's degree student, it was already obvious that this guy is going places. So we are not disappointed. You have over-delivered. And Annie, I love you. You are just such a wonderful person. But if I can summarize from my perspective the essence of Annie, it must be really a creative genius and her adventurous spirit. Maybe those are the two things that stand out for me. Annie as a person. And you can see that, she takes on a lot. And she delivers on all of it with flair. And she inspires many, many people along the way. And maybe something is a bit personal maybe, but Annie tends to underrate herself, which is quite surprising. Because, how many people do you know, how many women do you know who are professors in engineering, who has 3 kids under the age of 10, who has in the past 3 years undertaken twice a month-long journey to one of the most hazardous areas on the planet, to Antarctica and back, to literally hunt for treasure. Who plays the violin brilliantly, but also who is twice in the last 2 years run the beast, Cederberg, 42 kilometers, I think more than 2 kilometers up and down in terms of elevation and dips. You can correct me on that. But twice in the last 2 years has run that marathon. So I have to say, really, hats off to both of you. We are in the presence of greatness. Thank you. And then thank you for giving us an opportunity to celebrate. And I would like to invite all the friends and family, and colleagues and students who are here physically to join us for a drink and something to eat. And I want to really say thank you to everyone online, collaborators, students, parents, friends, colleagues, everyone who's watching online. Thank you for making the time to join us for these fantastic 2 presentations. Thank you.